morning, everyone. Today we're going to pick up with confidence intervals for our simple linear regression. Typically, you would gather data and enter it into our spreadsheet, and you would create your scatter plot and your regression line. You would check your quantile plot. You would look at the residual plot. One of the things you need to consider is that because we're working with a sample, we don't truly know what the standard deviation is. So that tells me that I need to convert now to a t-distribution, and we're using an n-2 degrees of freedom. And we'll talk about that in a second. So in our original regression line, we used V1 to represent our slope. This is going to be our point estimate for beta 1. So we'll still use that from the sample, but it's going to be our unbiased estimator for the regression slope. So this is the formula we're going to use for a confidence interval. We're going to use slope as our point estimate. And you can see we would sub it in right here. The rest of this should look familiar. The structure is basically the same as all confidence intervals. You can see we're using a t critical value. And then we would need the standard error for the slope. The degrees of freedom here, n-2, one is for the intercept and one is for the slope itself. So we're using 2 degrees of freedom. We can also run our significance test on the slope. So if you're setting up the null hypothesis, we're saying that the slope is essentially 0. We're going to run a t-statistic, so you'll use the slope, and then we'll divide it by the standard error for the slope. And you can see right here, we're using the 2 degrees, one for slope and one for intercept. When you set up your alternative hypothesis, we can have one side where it's greater or less than, or we can have a two-sided alternative. And when the upcoming example shows up, you'll see that that's what I did. When we calculate the test statistic for our slope, it basically will tell us if the slope, or if there's evidence that the slope is 0, or if it's not. If the slope is 0, that tells me that there is no straight line association between our explanatory and our response variable, and that creating an equation would be useless because there's no way to predict when you sub in. If you had to run a confidence interval for the intercept, which is beta sub 0, you could run it the same way that you do for beta 1. But in reality, we don't have a use for testing our intercept. It has little significance in statistics, so we won't ever really do that. We will stick with testing our null hypothesis on our slope, beta 1. All right, so let's run through this example. It says infants who cry easily may be more easily stimulated than others. This may be a sign of higher IQ. Child development researchers explore the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. A snap of a rubber band on the sole of the foot caused the infants to cry. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the children's IQ at age 3 using the Stanford-Binet IQ test. A scatter plot and Minitab output for the data from a random sample of 38 infants is on the next slide. Do these data provide convincing evidence that there is a positive linear relationship between crying counts and IQ and the population of infants? So the first thing you would do is enter your data into a spreadsheet so that we could see a scatter plot. We can see the cry count would be the explanatory variable and the IQ is the response. I think that this data looks moderate. I don't think it looks very strong, but they did place a least squared regression line into the data. So it looks like it's got a positive relationship. This is the Minitab output, and we did see this in an earlier slide. So the constant is your intercept. This is beta 0. The cry count is your slope, b sub 1. These coefficients are the numbers that are present in your least squared regression line. And we'll look at this other information in a little bit. We also want to check the residual plot. So the residual plot does look scattered. So that would be a good sign of a linear relationship. And then the normal quantile plot does look fairly straight. So by looking at these graphs, we have met the assumptions and inference would be appropriate for linear regression. So do these data provide convincing evidence that there's a positive linear relationship between the cry counts and the IQ? We're going to run a significance test. So we're going to start by stating the null hypothesis that the slope is 0. And since there was no other evidence in either direction, I'm going to run a two-tailed test. So I'm going to say that the slope is not 0. And we're going to set alpha at 0.05. So I'm going to start with my formula. Notice it's a t-test. We're going to put the slope in the numerator and the standard error in the denominator. You can go back to the Minitab output on the previous slide, or you can look in your packet. We're just going to sub in the values they provided us. So there's my slope and my standard error. And when we do our calculation, we get a t-value of just over 3. So that right there is pretty significant. We're going to come up with our p-value. We want to run a t-CDF. You can leave the lower bound at -infinity. Our upper bound is our t-score. And remember, degrees of freedom is n minus 2. There were 38 infants, so we're going to use 36. And this is the p-value that was obtained. But remember, that was in the upper tail. So we want to do 1 minus our result. And then we're going to multiply by 2 because of the two tail. And we can see that 0.004 is less than alpha. So we do have significant evidence that the higher cry count does result in a higher IQ. We're going to make our statement. So I said there is significant evidence at alpha equaling 0.05 to conclude that the slope is not 0 and there is a linear relationship between cry count and IQ. So I just wanted you to see the Minitab output. We were using the coefficients in our least squared regression line. And then when we were subbing into the t-test, we used the coefficient for cry count and the standard error. But you can see they had the results of the test of significance. And this is the same value that we obtained for p as well. Now we want to calculate the 95% confidence interval for the same set of data. So this is our confidence interval structure. Our point estimate for beta 1 was provided as the coefficient for cry count. And there's the standard error. We do need to come up with our t-critical value. So just to recall, on the calculator or iPad, we want to use an inverse t. Even though it's a 95% confidence interval, we're ignoring the lower tail, so we're using 0.975, and degrees of freedom is 36. So this is the t-critical value that was returned. So we'll sub that in. And I'll calculate the t-star times the standard error. And we'll get our upper bound and our lower bound. And we can see here that 0 is not part of the confidence interval. So because it's not part of the interval, that's just further evidence against the null that the slope is not 0. And likely there's a linear relationship. In addition to our inference testing on slope, you might be interested in certain values that are mean responses when X takes on different levels. So what we would see is future observations and what values they might look like. We'll look at these in depth later on in the unit, so these might not make a whole lot of sense right now, but you can come up with a confidence interval for the mean response when X takes on any value. So we're using X star, but basically we could say X star is 3 or X star is 10. So what we would do is come up with a certain point estimate, and then we would run the confidence interval. Structure is still the same. You're going to need the standard error, though, mu. Again, we're still using n minus 2 degrees of freedom. On the next slide, we're going to look at how you would calculate the standard error from mu. And we won't be doing this today. But to calculate the standard error for the mean response, this is the formula you would need. This is on your formula card on page 3, up at the top in the left side. The calculation, though, of the sample standard deviation is going to come from here. We would have to look at all the residuals squared, sum them, and then divide by our n minus 2 degrees of freedom. I'm going to give you the calculator keys. Until we actually do an example, this won't help you. When you enter all the data into the spreadsheet, they actually create a residual list that you could examine. So the order in which you input the data, they will also give you a residual list that is matching. So whatever comes first, the first residual will pop up in a list. So this might be helpful when we're trying to create this later on. This formula, even though it's on the formula card, sometimes it's difficult to calculate, especially if you have a lot of observations. So when you're looking at this denominator here, x sub I minus x bar squared, and you're trying to sum all those residuals, we won't have the data. We might just have certain aspects of the problem. So what I found is this. On your calculator, when you input the data into the spreadsheet, you'll be provided with the sum of x squared, and then you'll be provided the sum of x's squared, and they're different even though they don't look different. All these pieces will be on the output in the spreadsheet. So you could modify your formula. I actually like the Duke alternative better. Again, we're modifying the denominator to match the information that we'll probably be presented with. So if you want to change a formula card, I would use the Duke alternative, but I would change my denominator. This information is likely to be present, and that will be helpful. And even though we're not going to calculate a confidence interval for any given point at this time, what you can see here is in this diagram, in the scatter plot, the solid line is our least squared regression line. The two dashed lines are a confidence interval. So you can see that the confidence interval is wider at the two ends, but this is for some predicted value of x star. So we can just see how that's being modified. And at the ends, there would be more variation because we're nearing the bounds of the graph. There's no homework for this section of our notes, but you're welcome to call me or text me or send me an email if you're working on something older. Otherwise, have a great day.